First things first today, welcome back. Hope everybody had a good weekend. Hope everybody got to relax a little bit. I know you guys had some stuff to do on Friday. Did anybody take a look at those YouTube videos we sent you? Yeah, basically I'm asking if you did your homework. It's fine.
It's with assignment 8, you guys. So the YouTube links were included in assignment 8.
Yeah, so if you, again, assignment 8 is something you can be thinking about now. It's the what do I want to do when I grow up assignment, right? Take some time and watch those. Like, you guys will see, again, I know some of you guys have mentioned wanting to go to the grad program with us, and that's awesome. Those videos, you know, we talked to Scott Branham in one of them, and Scott's very engaged at WVU in a lot of different ways, but Scott's somebody who came from a non-technical background and wanted to learn more about technical so he could help his organization, right? Scott Branham will tell you straight up, and I know this is being recorded and I don't feel bad saying it, he is not the most technical person we've ever had in this program. But what he knows how to do is create value off technical now, okay? You're gonna meet Kaylee Matala. Kaylee was MIS and then came into BUDA our first year. Kaylee's held a bunch of different jobs now, but she's grown and she's become a rock star in the field. She's with United Bank now. She spent some time doing software engineering stuff as a data scientist at Leidos. Like, she's been all over the map. So she's a real cool one to talk to. There's the panel that Kristen and Catherine ran on banking. You know, there's so many good people on that one. I'm not even going to go through the names on it, but you know, Brennan Comfort was on there. Who else was that?
Jillian and Bill Robertson.
Oh yeah, no, those are 3 awesome ones. You definitely have to watch that one. And then I threw one up that I wanted to talk to you guys about. Just because I think one of the things, and this is going to lead into a second piece of the thing I want to tell you about today. The first thing is, you know, there's another video up there with a guy named Pete Gibson. Pete has been CIO of a lot of different companies. Wyndham Hotels being the first one, CIO, CTO, so Wyndham Hotels. But also, have you guys ever heard of the restaurant Fridley's and Johnny Rockets? He ran those during COVID. You want to figure out how to use technology as a strategic advantage. Have your dining room cut off in a restaurant, right? Pete talks about some really cool stuff. He's done a lot of stuff in the mix of hospitality and tourism and technology. That's been his kind of go-to. I worked on with some projects with him for like Hertz in kind of strategic placing cars and stuff like that. He's a great guy, great person in general, but has some really cool insights on just the transition and the different training and what we're going through there. So I definitely keep an eye on that. The other thing I want to put on your all's radar is tonight at 6 up at Vantage Ventures, John Chambers is coming to town. If you guys wouldn't have been around to hear John speak before this, you guys, again, maybe if you were a senior, you heard him one of the first times he was on campus. I'm going to go up there and listen because I always come back from hearing John talk. Inspired would be, I think, a good word. He knows how to control a room, but also he's just a really smart guy talking about hard problems, right? And he's from here. He has a lot of passion for here. So again, if you guys are up there, you see me sitting there, feel free to come sit with me, come say hi, do all those things. All right. But again, I put that on your radar. It's not required, but it's something you should think about if you have time, because it's always a cool event. All right. And the one thing I would tell you is don't walk up there in jeans and a t-shirt like that. That's the other thing. If you're going to go to that one, like, business casual is not a bad thing. All right. So again, I would tell you go watch that because that could be a real cool conversation. Other than that, how's the homework going?
I got some emails about it on Friday.
Good.
Yeah.
I have a quick question.
Yeah.
So I know on the first problem we're supposed to pick, is it like rating or like we're supposed to pick one of the other variables?
Yeah.
But on the second problem, are we supposed to use both age and education, or are we supposed to pick one or the other?
Use age and education for me. Okay. Like, the first one, I'm giving you the decision point, right? And then the second one, I'm saying use the one I want you to here, and age and education. So in the first problem, you'll have 2 predictors. In the second problem, you're going to have 3. Awesome. Krish, I just saw your message. I have not seen a Zoom link to it yet, which makes me think there's not going to be one.
I
Or
haven't
it may
seen
be,
one either.
yeah, it may be recorded and posted after the fact, which is something they do. They don't want to worry about the live stream a lot of the time when speakers like this are on campus. For the simple fact that it creates just a little bit more chaos and you're trying to manage chaos in those situations. Right. So that's just one more thing that can go wrong. So mitigation of risk, right? Any other questions on the homework, y'all? Let me say it again, start the homework. All right. Like this is your daily reminder. I'm gonna say it again on Wednesday. You know, every day we get closer, it's still due Friday, right? It's still due Friday. Every day we get closer. All right. So again, start the homework. Make sure you guys put in some time and effort to it. Just as a reminder, I'm going to be out all of next week. Catherine's going to be running the show. Let's be honest about it. She always runs the show. I just talk a lot. But it's one of those things where you guys are going to be talking about some really cool stuff next week, and I want to make sure we get there. Okay. Hopefully we'll be able to introduce it a little bit on Friday as well. But I want to pick up where we left off. Let me go ahead and share my screen here.
Hey, Brad, while you're doing that, I did think of a question I got on Friday that would be helpful to everyone, and I'll put it in the email that I send out later today as well. When you are working on added variable plots or effects plots, if you're having trouble knitting, like if you get an error for either of those when you go to knit, try adding library ALR4 to your code beforehand, because while it might run locally, for some reason it was causing issues when trying to knit. So just helpful hint there.
And the effects plots and the added variable plots are in the car or effects library.
Right.
So sometimes if you load those directly, it helps as well.
Yeah.
So one of the things we talked about last time a little bit was, you know, we kind of left off in the Big Mac example, right? So we kind of said, hey, look, what we're going to do is we're going to fit Big Mac against log bread and log price. And that's what we called a residual plot, right? A residual plot is plotting the residuals of your linear regression model against the fitted values. Now, why are we doing this? Okay. Why are we doing this? Can anybody remember why I care what a residual plot is? I know it's been almost a week, so I want to make sure we get the gist of all of this stuff, because sometimes the details get messy. Why do I give 2 cares about this plot? See, what happened, Brad, was you talked, and that was a week ago, and there's been a lot of stuff happen. So help me out here. When we fit models, right? When we fit models, we're fitting models for 2 purposes. We're fitting models for prediction or for decision-making, which is what we call inference a lot of the time, right? Really, that's what we're getting down to. Do I need an output, or do I need to say this variable relates to the other? In prediction, I don't care about this plot. Now, it'll make my predictions better, but I can get by without it. When we're saying A relates to B, we're basing it on all kinds of assumptions, right? The assumptions, we have normality of the errors. The straight line we fit, the model we fit gives all the details. There's no relationships. The observations are independent of one another. And then there's constant variance. If those 4 things happen, those p-values we talk about in the linear regression model, those p-values we talk about when we fit a model work. Thought I had an example of it sitting right there. That's the reason I scrolled. If those 4 things are true, those p-values are honest. They're the right thing to do. But if they're not, you could be making a bad decision, right? We talked about it from the software paradigm. Garbage in, garbage out, right? What we're doing is we're testing to see if our data is garbage. You guys with me on that? And if it's not, we're trying to make it not garbage. Or if it is garbage, we're trying to make it not garbage. So what we do is we look at these plots. And just a reminder, this plot is our friend. All right, this plot is our friend. You guys are going to get sick of looking at it. I'm sorry about that, but get used to it. What I'm looking for here is I want this plot to look completely random. I want it to look like there's no trend whatsoever. If there is a trend, or if we have what's called non-constant variance, y'all remember what I talk about the non-constant variance as? I talk about the alligator mouth, megaphone, whatever you want to say, right? It basically says the vertical variation, the vertical variability, the vertical spread as we move across the x-axis should be the same. See how the vertical spread here is really small? Now, it's always going to be really small on the edges, guys. All right. Why? There's only one minimum, one maximum, right? There's not a lot of data there normally. But as we get into the middle, you see how the vertical variation here is small. And then as we keep coming across the fitted values, it gets much wider. Basically, it becomes higher variability as we move across that plot. Does everybody agree with me there? This is thumbs up, thumbs down, guys. This is the stuff we actually need to be talking about, all right? As you see that, that's the first thing that goes, I got a problem. I got to fix this. Now, the question is, why do you have to fix it? And this is going to be the hardest thing for you all, because it was the hardest thing for me, and it's the hardest thing for everybody who has to do this. I ran a regression model. It says two things are related. That's what I want. All right. Great. You're going to make a recommendation. You're going to put that one line on a slide, right? You're going to write up that paragraph that an executive might read. And your name's going to go on that. If you're wrong, what happens? That's a question I don't want you to find out. That's the reason we go a little bit deeper into this, okay? So again, when I see this, I got problems. Now there's a test to check for it. First thing you see here is I see that megaphone, I see that alligator mouse, I see that trumpet, I see, whatever you want to call it. I see a problem. Now what we got to figure out is how to fix those problems, okay? Now, when I transform the data, and how I transform the data here is I took a log. Now remember, we spent all day last Monday talking about logs and what they mean, right? And why we like logs and why we like the interpretation associated with logs. All right. So we spent some time on that too. And then we talked a little bit about testing for curvature. Okay. We talked about how things were related to one another. What I want to talk about now is I want to talk about how we fix these things. Curvature is a problem. If we see trends in our residual plots like this, what it means is you have curves in your data. You have a curve in your data. There's something you haven't fixed. That's easy to fix. I'll show you how to fix that later. What I want to talk about is how do I fix this? How do I fix this non-constant variance? Okay. Well, how did I fix it here? I took the log of a response. Remember, my model originally was Big Mac against log bread and log rice. And that worked great. Until I saw this. To fix it, I took the log of it. The question is, how did I know to take the log? How do I know to do this stuff? Well, there's the old adage. I've been doing it long enough. There's a saying, and I had a professor at Minnesota say this, and it's something that stuck with me forever because I feel like it's really relevant. When it comes to problems like this, there's impossible and there's trivial, okay? It's impossible because you don't even know where to start because somebody ain't showed you the trick yet. Once you know the trick, it's trivial. It's a read-react thing, okay? But what you're going to figure out here too is there's a statement I love in an intro stat book written by Alan Agresti. Alan was down at the University of Florida for a long time. And it basically says statistics is much of an art as it is a science. There's a lot of math going on behind the scenes here. You guys understand that. The art of it is, how did I know to take the log here? What we're going to do is we're going to look for mathematical indicators. We're going to read and react, okay? We're going to learn when our eyes are telling us there's non-constant variance. We have some tests for that stuff, but trust your eyes, okay? Trust yourself. One of the things you guys are going to gain in this class a little bit is confidence in your ability to do this. That's one of the reasons we have you doing RMDs and not point and click stuff. I need you to have the ability to do this. Y'all with me on that? So again, when we see something that looks like that megaphone, your mind goes non-constant variance. All right. Now we got to fix it. Well, I told you I took the log to fix it, but how did I know to take the log? Let's talk about that. So we're going to come down here. We're going to talk about fixing non-constant variance. Okay. Now, you've seen the non-constant variance test. All right. But the question is, how do we fix non-constant variance? We know if we can define a function of it, it's a simple function, then we can use this thing called weighted least squares. I'm not going to get into weighted least squares with you guys. You guys that are going to come hang out with me in 451, we'll talk about weighted least squares a little bit then, because it's a trick. It's a way to trick our line to have confidence in a prediction. But that fits more about that class than this one. All right. But what we can do is we can use what's called variance stabilizing transformations. All right. Variance stabilizing transformations basically say, hey, there's something that's going on here. We can relate this to a function of the mean. Now, if you guys think way back to when we talked about logs, you saw something that looked like this, because look, I said, read this. It turns into a percentage increase. What it says is the variance is based on some function of the line. That's all that says. I write that down. I leave that there to show you this one part. All this is telling you is the variance is based on some function of the line. Okay. Now, the idea when this happens is I want to transform my response to something I'm going to call YT. So when you see that big T under there, that means it's a transformation. Okay. I took the original data and I turned it into something else. You guys with me on that? This is a transformation. Taking the log of Big Mac is a transformation. All right. So let's talk about what transformations are available to us. All right. All we're saying is this is approximate. All we want is approximate equality of variance. We want approximate variance equal. So the variance of YT, my transformation given X, is now approximately constant. It ain't ever going to be exact. All right. Now, there are certain cases we know we're going to use square root of Y as our transformation when the variance is about the same as the mean function. That means it's a straight line. All right. Now, let's talk about square roots for a second. Can I take a square root of a negative number? If I got, let's try this. What's the square root of 4?
2.
2. There we go. All right. Square root of 25. 5. All right. I like it. Square root of -2. Yeah, we ain't talked about that one in algebra, right? That's not one we really got into too much. Now, for my guys who are a little bit more advanced mathematically, you know there's things called imaginary numbers. I prefer to forget those exist. Okay, we just ain't gonna work on them. Those can remain imaginary. Those can stay out there with my 3-year-olds, like PJ Masks and like all that fun stuff that comes off Disney, right? We're gonna work on reality for a second. Reality is negative numbers don't have square root. Not that we're gonna use anyway. But now let me ask this next question. What's the square root of 0?
Zero.
0.
Just be 0.
Yeah, it's just 0. So why do we talk about this? Is because a lot of times in the data we're going to use in business, numbers are always positive, but can be 0 at times, right? Square root of 0 exists. Remember when we talked about logs, does log of 0 exist? Y'all, here's the cool thing about always working on a computer. Log of 0, that ain't a thing. Negative infinity is a concept. It's not a number. All right. So what we're saying is, look, this has to be strictly positive, or excuse me, this has to be non-negative. Non-negative. So whenever we want to look at square root of Y as an option, it cannot be negative. Are you guys with me on that? That's really important to keep in mind. All right. Now, if counts are small here, we can adjust it one more time. Like if you've got really small numbers, here's another trick. You can take the transformation and make it square root of Y plus square root of Y plus 1. So if you got a lot of zeros in your data, what that'll do is that'll just shift it just a little bit more. You guys with me on that? Or if they're really, really small numbers like 0.005. So imagine you're doing an analysis in hundreds of thousands and you've got some stores that have only hit tens of thousands, right? We can use that as a little trick as well. Y'all with me on that? All right. Next one, log. I think we spent an entire class period on log. First rule, Non-negative means it has to be greater than 0. All right. This becomes my best friend. This is my go-to. When I see something wrong, my default is to try a log transformation. Y'all want to know why? We talked about it last Monday. It has this pretty interpretation, right? It has this percentage increase interpretation. It talks about realistic things we can see, like discounted pricing structures. Oh, well, we wound up getting it for about 20% of the actual value or 80% of the actual value, right? When we talk about those things, when we think about those things, that's the reason it's our go-to. It has an interpretation. You'll hear me say it over and over again as we go through this. Don't ever fit a model you don't want to interpret. Because you're going to throw it up there on a slide and you're going to say, here's what I came up with, here's how, and somebody's going to go, what's that mean? Because that's your job to know what that means, right? So you got to be able to lay it out there to them. Y'all go with me on that. The other one we can use is called an inverse transformation. All right. Inverse transformation. It's just 1 over y. All right. This can occur when the values of y are close to 0, but large numbers can occur occasionally. Remember, I just walked you through that store example. We've got a lot of things that are in tens of thousands, but then we've got a couple stores that may be in the millions. That's a big difference. All right. And then you guys want to really get into your trig class for a second. We can use the inverse sine of the square root of y. I have used that twice in my career. All right. But it's when somebody gives you proportions. Okay. If your response is ever a proportion between 0 and 1, but they're giving you percentages basically, because that's what a proportion is. Everybody agrees, right? You can use it. All right. We call this the arcsine square root transformation. Now, there's other options, and we'll get into it if you come hang out with me in the master's program. But for right now, this is what we're going to focus on. You guys good with that? Specifically, there's 2 I care about, and I've used more times than not. It's these. Okay. This one's useful every now and then, but my go-tos are right here. If I don't like something, square root. If I don't like something, log. I use log first, then square root, as you guys will find out as we go. You guys good with that? All right. So let's talk about this fuel data example for a second. Now, what I'm going to do is I'm going to load up some data here, and I'm starting on line 196. We're going to fit this model. All right. And just a reminder of what this thing is. Look at me not being prepared for class here. Let's fit on this now. All right. All I'm doing, just a reminder, let's do help fuel 2001. That's a long time ago. But just a reminder of what this is. This is data on motor fuel consumption and related variables for the year 2001. The unit is a state in the United States or the District of Columbia. All right. This is number of licensed drivers in the state. Fuel C is gasoline sold for road use in thousands of gallons. All right. Income, miles, MPC. MPC is just estimated miles driven per capita, population, age 16 and over driver's licenses, and gasoline state tax rate in cents per gallon, right? And remember, we talked about this when we talked about effects plots, because we said, look, what is actionable about this? And what we talked about is how income actually affects fuel, or how tax rate affected fuel consumption in different places, right? Now, what we want to talk about here is what's going on. So I'm going to fit this model. And right off the bat, I'm going to take the log of drivers and the log of miles. And we'll talk about why I did that here in a second. All right. I want to start looking at a residual plot, though, to see what's up. So I'm going to run this model. And here's my residual plot. So what do you see off this residual plot right off the bat?
Curve.
You see a curve. Do you see constant or non-constant variance?
Wouldn't that make it non-constant then?
If I have a straight line, right? If I have a dotted line that is just a curve that comes across this, right? Let me give you an example of that. See how that kind of looks right there, where it's just a curve, but it can have non-constant variance, right? That's what we're talking about. So in this case, we're getting both of these things. Would you agree with that? There's a curve there in your eyes, but there's also non-constant variance that comes across it, right? So again, you got two problems. What do? Pick one and try and fix it. All right. You got two problems. Let's try and fix one and see if the second problem's still there when it's gone. You guys with me on that? All right, so let's go. So first thing I'm going to do, I'm just going to try some stuff. I know that sounds real mathematical, right? Sounds like real process driven. But what did I tell you my process was? Try log, then try square root, right? Why? Because it's what works. It changes the behavior. This is coming from the fact, Sam said it a second ago. Samantha said it a second ago. There's the curve here, right? That means it's a nonlinear function. There's non-constant variance here. That means the variance moves with the expected value. Right off the bat, based on what we've talked about with logs last Monday, and based on what we've talked about just by curves, that should tell us log should do something. Now, I'm going to teach you. All right, I'm going to teach you a piece of code we will be using for the rest of the semester. You will be using it for the rest of your time in R. It's called par mf row c or equals c2 comma 2. Par opens up a new plot window. MF row creates a plot grid. Row, then column. What this is doing is creating a new plot with 4 subplots in it, a 2x2 grid. You guys with me on that? So when I run this, watch what happens. It went 1, 2. All right. See how it didn't fill out the bottom here? Because there's 2 other plots waiting. You guys with me on that? So if I do this as 2 comma 1, it should do 2 rows, 1 column, right? If I do 1 comma 2, it should do 1 row and 2 columns. Are you guys with me on that? So let me show you a couple things here. I got to highlight it all so we can look at it side by side. Be better, Brad. Now check this out. First model, I took the log of fuel consumption. Didn't change anything else, just took the log of fuel consumption. Y'all with me on that? Created the residual plot. This is the left-hand panel plot is the log of fuel consumption. Y'all with me? All right. Square root of fuel consumption. That's this plot. Now I want you to take a look. That's our original plot. You guys with me on that? That's if we do nothing. So this is do nothing. Take the log, take the square root. Don't let the blue line fool you. Ignore the blue line. Actually, given the 3 choices and the blue line, which one you picking? And I'll give you a 4th choice, none. You choosing do nothing, you choosing the log, you choosing the square root, or you choosing none.
I mean, the log looks the best compared to what it did.
So you're saying if I only gave you 3, you choose log. Is that blue line trying to tell you something right now? Or are you ignoring it?
I mean, it's trying to, I mean, if we're just ignoring it, it looks fine. But if we're not ignoring it, obviously there's still something wrong.
Ignore the blue line. That blue line is trying to reach points here that don't need to be reached. Remember I told you what happens on the edges. It's always going to look a little weird, right? Never going to look perfect. Why? There's only certain minimums and maximums. Factual statement about a data set. There is only a single value for a minimum or maximum in any data set, right? You could have multiple points there, but there is only one value. And typically we don't see many minimums or maximums unless it's a weird process, right? So again, what it's trying to do is it's trying to reach down here and grab these things. That's whatever. I'm looking at this and I'm going, ignore the blue line. Does it have constant variance? Yeah, that spread's pretty constant. Does it have randomness all over it? My eyes don't see a trend. That meets the two things I asked it to, right? No trend. You guys, when we looked at this before, you said there's a curve here, that's a trend, and there's non-constant variance, right? Visually, I just went, there's constant variance, and there's not a trend. Call it a day and go. What do y'all say? That's what it is. That's what you're doing here. We ain't looked at a number yet. You guys agree with me? This is called Intro to Data Mining and Visualization, right? Here's your first trick of visualization. You want somebody to see a trend, put data in a line through it. I don't care what that trend tells me right now. I need to validate the trend myself. Would you guys agree with that? I'm good going with log. What about y'all? Anybody got an argument against it? Y'all allowed to argue with me. Just because we teach it doesn't mean I don't mind. I mind when y'all argue. All right. This is your process. You go, oh no, something's wrong. Try some stuff. The thing I will tell you, okay, where people fail in this is because they're scared to try something. Do something. All right. When you see something wrong, try something. It may not fix it, but it's going to take you down a rabbit hole. You will hear me talk about your process and what you do. My process is I see a problem. I try something. What do I try first? I try log. Why? Because I like the interpretation and I don't want to fit models I can't explain. I try square root next. Why? Because I didn't have to give you guys an algebra lesson on what a square root is, right? We had some basic questions just to jog your memory about what square roots are, right? It says what number times a number makes that number. What number times itself makes the other number, right? That's what a square root is. Square roots, people feel like they can understand. They're real happy about it. You start taking the arc sine square root transformation, you let me know how that goes in the boardroom. First rule of it is don't use it. All right. Now, a couple other things as we go here. Excuse me. Got something in my eye. All right. When I run residual plots, now notice the difference in the code. This is residual plot, and this is residual plots. Now, remember I told you, we can look at this just for the fitted values, right? But we can also look at it for every predictor to see if a predictor is the problem, okay? The predictor being the problem is my concern. We just tried transforming the response, right? Look at my model. I just changed the transformation on the response. I didn't need to touch tax. I didn't need to touch drivers. I didn't need to touch miles. I didn't need to touch income to get it to meet the assumptions. Do you guys agree with that statement? Here's your second rule of my process. This is mine. Yours might be different, and that's okay. Y'all allowed to think for yourselves. The second rule in my process is fix the response first. You're going to get really complex stuff going over on the right-hand side here. You're going to get really complex predictors going on that right-hand side. Fix the response first. Why? There's only one response. There's only one place to mess with there. We go to this right-hand side. There's 1, 2, 3, 4. Oh, no. Life just got more complex. My philosophy is KISS. Keep it simple, right? Now, there's another S in there, but this is class, so we're not going to say it. Keep it simple. If I can work on the left-hand side, there's only one thing. If I want to work on the right-hand side, I can put as many predictors in the model as I want. but there's only one thing on the left-hand side always, right? There's only one response in all these models. So keep that in mind as we go. All right. So this gives me a comparison with everything. We'll come back to this type of a plot later, but I just wanted to show you the difference when we put that one letter in there, when we get that one S in here. You guys with me on that? All right. Now, marginal model plots. This is where stuff gets fun. Y'all having fun yet? I am. That's why I got into this stuff. I'm a little bit crazy, y'all, if y'all haven't figured that out. Now, a couple of things I want you to see. Our discussion to this point is to see how well the model matches assumptions we have made on the data. We can augment the model to meet this criterion. A second and just as important question is how well does the model match the data graphically? In the SLR setting, we can fit a smoother or regression model to our model and see if the two models agree to a certain extent. Now, all a smoother is, you'd hear me call it, let the data fit itself. Basically, all it does is it picks a neighborhood and it says, what's the average here? What's the average here? And moves across. All right. What I'm going to do here is I'm going to use some data from cedar trees. All right. And we're just going to look at the height versus one of the predictors. All right. Just to show you what's going on here. Now, here's the smoother. The blue line is a non-parametric fit. Non-parametric means you can't interpret it. That's the first thing you got to understand. Non-parametric, it's a cool idea in statistics, but it means there's no model. When we work in industry, one of the things we have to have is we have to have a model because we've got to try and be able to explain things. You guys agree with me there? So if we don't have that model to use, there's no interpretation. It's just straight prediction, which is cool. Like, guy who makes a living off making predictions is fine with predictions being made. But a lot of the time, somebody's going to ask you is, are these things related? What's the impact of that? Non-parametrics don't set up for that, okay? The red line is my model. The blue line is the model if we let the data fit itself. And by that, I mean, just create some weighted averages as we move across and say, where would the weighted average be? Does the red line fit close enough with the blue line for your liking? This is what a marginal model plot is. It basically says, how well does my model work? All right. It says, how well does my model work? Now, let's take it one more step. Let's go back and let's look at our log fertility against log PPGD % urban model that we've been messing with. What it does is it breaks down each of the effects, okay? It breaks down each of these effects. Remember the effects plots we looked at? Talking about the growth. What this is how does log fertility move with log PPGDP based on the data and based on the model itself. How does log fertility move with % urban? And then how does it compare to the fitted values? Each one of these is pretty good. Wouldn't you guys agree? This isn't residuals. This is the actual response itself, okay? Would you guys agree that fits pretty well? The blue line and the red line are pretty close to each other. For a linear regression model, that's a heck of an approximation. Would you guys agree there? What this is a visual assessment. And we can get it in one line. Remember how I told you when models get big and complex, they get really hard to plot? What is it you see we're doing? These are just effects plots, y'all. Remember I told you effects plots are a big deal, right? Why did I tell you they're a big deal? Because they help you tell the story about a single variable in a complex model, right? That's why we like effects plots. Effects plot said, if we move this variable like this, here's how we expect the response to move. You guys remember those conversations? If you don't, your homework's going to jog your memory. Promise you. There's a reason we give it. And y'all going to start to see this. The stuff you're working on homework, that's what I'm going to use to talk about in current context. I know sometimes this looks like chaos, but there's a method to the madness, y'all. Here's the idea. I can use these. I would never show these to a client, but what are they doing for me? They're confirming I'm not crazy. They're confirming what I'm doing is a decent model. Would you guys agree with that statement? Red line, blue line close together, things are good. Red line, blue line far apart, things aren't so good. Y'all good with that? Again, it's one more tool to assess what you're doing. All right. I can add one more feature. I can add one more feature, and it's SD equals true. And what it does is these put confidence intervals on these for me and looks at how the confidence interval bands move together. Y'all, that's a single model. Blue lines and red lines matching pretty well. Would you guys agree with that? That's a pretty good model. Ain't bad for 2 predictors, right? But it can talk about the overall trend and the variation of the data. All right. Now, overall in this section, and I think this is true of anything we're going to do, it's one of the more useful things we do in the field. So to do any kind of inference in regression, we need to check the assumptions of, is the mean function 0 and is the variance constant? Basically, does that plot look random and does it have constant variance? That's all we're checking there. Y'all with me on that? We talked about using a log and square root to do a couple transformations. But what we really need to do is we need those 2 assumptions plus the normality assumption, which we'll talk about in a minute, to say, look, the things I'm getting ready to talk about, the relationships I'm getting ready to look at my boss and say, yeah, I'm in on that. I'm verifying that. All right. I'm in on that. I'm verifying that are true. Again, and I've told you this before, if you're working in analytics, you're working in what I call a service industry. All right. You don't create things. You analyze things. You provide insights. You provide value. There will be days when the janitorial staff provided more value than you did. Not saying that job's not important, not saying it's there. You guys are going to provide value. You have to. But you have to make sure it's the right thing. You're going to have to learn, especially at a young age. And I still struggle with this, y'all. I've been doing this a little bit. I still struggle with this. Balancing speed with rigor. I always want the answer now. I want it quick. That thinking can lead to bad analysis because you got to do your work. Okay. You got to go in. You got to think about this stuff when you're fitting models. You got to think about how you're going to assess it. You got to think about how you're going to communicate it. The thing people who work with me, and Catherine and Kristen will both tell you this about me, and Hannah with Data Driven will tell, like, she'll rant about this on me, and it's very well deserved. I go fast. I go very fast. I have an expectation of the people around me to catch up, especially over the past 18 months. But what it leads to actionable insights quick. But the thing I've learned to do myself is slow myself down to make sure I'm doing this. That's the reason I talk about this as a reproducible process. I'm not teaching you how to analyze a single data set. I'm teaching you a set of skills to attack a problem. You guys with me on that? When you start, don't try and go as fast as me. I shouldn't try and go as fast as me, but you sure don't. We'll slow down, okay? What I'm doing right now is just showing you the tricks. Y'all with me on that? These are the tools we're going to use. And then we're going to spend a couple of days just attacking problem after a problem so you guys can get used to the process. You guys with me on that? Let's spend just a couple minutes here talking about general transformations. All right. Just what's going on here. Now, these transformations, I've told you, we can use log and we can use square root, and you should try and use log and square root. But there's some other tools at your disposal. And one of them is called a power transformation. Okay. So let's take a look at something really cool that everybody can understand. The relationship between body weight and brain weight in animals, because that comes up in business every day, right? But I think this is a really cool plot to show you what's going on. These are mammals. All right. Here's the brain weight and here's the body weight of mammals. First question is that a linear function? Is that a straight line? All right, that's the easiest question I've asked today, y'all. Is that a straight line? Hey, there it is. I got a thumbs down on that one. I appreciate that. Now, here's the thing. How do we figure out what to do with it? Well, the first thing you guys are going to say is log and square root, because that's what I talked to you about 2 minutes ago, right? Try the log, try the square root, because that's what Brad said works. Sort of. We've got these other things that work, and it's what we call a family of transformations. And basically it says is I can take any function, this psi function of u and lambda, and a power transformation is u to the lambda. Now, let me tell you why this works. Lambda equals -1, that's an inverse. Lambda equals 1, that's don't do anything. Lambda equals 2, that's square it. You guys with me on that? We like those numbers, but we add one more thing to our power transformation family, because u to the 0 is 1. In a power transform, if we choose lambda as 1, it's actually a log, okay? It's a real cool way. There's a lot of math that goes on, but we raise it to a power, and if that power is 0 when it comes back, that means we do a log. Y'all good with that idea? Why are we using this? Because it creates a framework for us, all right? Now, I'm going to show you some differences here, okay? I'm going to use the inverse, I'm going to do the log, and I'm going to do the square root, and then I'm going to do squared, because u to the 1/2 is square root, right? Power to the 1/2 says take the square root. Take a look at what's going on here. This plot is brain weight squared and body weight squared. This is square root of brain, square root of body. This is inverse of brain, inverse of body. What worked the best? Out of those 4 plots, which one are you taking?
Second one.
Top right?
Yep.
Is that what we're calling the second one? Yeah. So my question is now, is that a straight line?
Pretty straight.
Enough for us, right? We're not looking for exactness anymore, y'all. Close enough is going to work really well for us. That's that log-log transformation we talked about last Monday. That's in our power transform family. All right. There are 2 rules, and this is where we're going to stop and pick up. These are the the 2 most important rules I will teach you, because you guys are asking me, why does log work? Why does log work? Why does log work? Do your work early. What do I mean by that? What's the first thing we're supposed to do when we start working on a data set? Plot it and look at summaries, right? You already know where you're heading with it, but plot it and look at summaries. You're going to have these 2 rules of thumb, as I call them. The log rule of thumb. If the values of a variable range over more than 1 order of magnitude and the variable is strictly positive, then using a log transformation will likely help. The range rule, if the range of a variable is considerably less than 1 order of magnitude, then any transformation is likely not to help at all. Basically what it's saying is if the max is 10 times bigger than the min, do a log. If it's not, and it's really, really close together anyway, you ain't transforming anything. These are our extremes. So take a look. The minimum brain weight is 0.14, and let's just call this pounds. Might be kilograms, but for discussion, let's call this pounds. 0.14 times 10 is a lot less than that maximum of 5,711 on brain weight. You guys agree with me? Right there. The second I looked at summary statistics, I knew I was taking a log of that thing if we were modeling. Body weight, 0.005 versus 6,654. 10 times that number is a lot smaller than that maximum. You guys agree with me? So right off the bat there, I'm taking logs of these things. From the second we would have opened this data set in what we're going to talk about, I was taking the logs of these variables. Y'all with me on that? That's going to be my go-to trick for everything we do, okay? When we come back on Wednesday, we're going to talk about transforming the predictor a little bit and then do some examples. Y'all good with that? All right. Y'all have a great day. Have a great weekend. Let us know if you need any help on the homework, all right?
Hey Brad, did you get my direct message?
Yes, I did. Thank you for that.
Yeah, Catherine calls me Sam.